Lesson 4-5, Reflection and Standing Waves. When a wave encounters a stiff boundary, such as a wave bouncing off a wall, the wave will reflect from the boundary. Waves obey the law of reflection, which says the incident angle is equal to the reflected angle. And so what we're saying here is, if this is a reflecting surface and a wave comes in this direction, what it will do is obey the law of reflection, which says that the angle of incidence is equal to the angle of reflection. And I've drawn theta. This is the symbol theta. Theta I, or incident, is equal to theta r. Those two angles would be the same. Now, the incident and reflected angles are measured with respect to a line drawn perpendicular. So this line here, this dotted line, is actually perpendicular to the reflecting surface. It's called the normal. And notice that angles x and y are also equal to each other. If you did this mathematically, you would find, but we generally measure the angle with respect to the normal. All right, so that's the law of reflection. Very simple little law. So understanding reflection helps us to understand the concept of a standing wave, because we know that waves reflect from surfaces. When a wave pulse encounters a stiff boundary, the wave will reflect from the boundary, and the reflection will be upside down. So if a wave comes in with the crest at this point, when it reflects off this reflecting surface, it will actually be upside down. All right, so it'll be inverted as it's reflected. So when a wave train hits a boundary, the reflection interferes both constructively and destructively with the incident. So what we're saying is, some waves are coming in and some waves are going to be leaving. So here is a wave train that's moving to the right, and it's going to reflect from a boundary. All right, and as it reflects from this boundary, the reflected waves, here's a reflected wave here, here's the parts of the reflected wave. What they do is they interfere both constructively and destructively. So at this point, they're interfering constructively. You get lots of displacement. Here, they're interfering destructively, and wave crests are meeting wave crests and are troughs, and they cancel each other out. So there are some points where you get constructive interference, and other points you get destructive. This is known as a standing wave. All right, so you get antinodes, you get nodes. This is called a standing wave. All right, so you can set this up on a slinky or some other device just by oscillating it back and forth. And many musical instruments rely on standing waves to create a certain kind of sound. So standing waves are useful in the study of resonance. Resonance can affect musical quality, overtones. It can even affect the suspended bridge integrity in high winds. All right, if you have ever seen the Tacoma Narrows Bridge disaster in, I think it was in the 30s, the bridge was built, and 3 or 4 months later, in a high windstorm, the bridge collapsed because a standing wave was set up by the wind passing along the bridge and caused the bridge to collapse. All right, so you can probably look that up on the internet fairly easily. So one important consideration of waves is that the nodes appear each half wavelength, as do the antinodes. So if you have an incident wave, notice that the incident wave, I'll just draw the crests of the incident wave. Here's a crest, and here's a crest. So we can see how far the crests of the wave are apart. All right, they're this distance apart. Now, when the reflected wave returns, of course, it's going to be inverted, and you're going to get nodes and antinodes. So here we have the crests, and then, of course, as the reflected wave comes along, notice that you have a node here, and a node here, a node, and a node, and here's actually another node, and they even consider this to be a node at the reflecting point. Notice how far the nodes are apart. The nodes are only half apart from one node to the next is only half a wavelength. And of course, between the antinodes, here's an antinode, here's the next antinode, notice that they are only half a wavelength apart, because we already established that this is a complete wavelength. All right, from the red here to the red here, that's a complete wavelength. So notice that the antinodes and the nodes are half a wavelength apart. A very important idea when it comes to standing waves. And standing waves are, of course, important in many, many applications. Even in chemistry, when we talk about the Bohr model, one of the reasons that the Bohr model works is because the electrons, which are particles, have wavelengths, and those wavelengths can only exist where you have a standing wave. And so scientists are actually able to look at the wavelength of those standing waves, a little bit more about atomic structure and about the whole idea of what matter is really made of.